Radio Galaxies by AJ Hedge.
Hi everyone, I'm AJ. I'm a PhD student under Nick Seymour over at Kern across the road. And this talk is going to be on some work which has been largely done as part of an SK internship under George Heald as well. So I'll get started. First, I want to do a little bit of a summary of kind of how we've looked at high redshift radio sources over the decades. And to start off, some of the high redshift radio galaxies we've seen have been the highest redshift sources known at their given periods of time. Back in the 60s, we had some sources like 3C295, and progressively, radio galaxies and quasars tended to be the most dominant sources at high redshift compared to optical and infrared galaxies. But then it's kind of all had a big change at this inflection point where HST was launched and then started collecting data on deep fields, and then optically selected galaxies started to catch up very quickly. And then similarly with the advent of JVST as well, you have a huge jump in these optical and infrared galaxies, which found it exceedingly higher redshifts, whereby in comparison, radio sources such as radio galaxies and quasars were left in the dust. But they're still important and we still care about them. One reason is for the 21 centimeter forest, and I will defer you to Nick's talk tomorrow for that in the EOR session. So if we care about them, how do we find them? Right. As part of work that's been done previously to me from Nick, Guillaume, and some other people who are at or formerly were at Curtin Cara from the last 10 years or so. They looked for redshifted compact deep spectrum sources with hints of spectral flattening or turnover below 100 megahertz. And so this is done primarily within GLEAM, with MWA. And so we expect that young radio galaxies at high redshift with compact steep spectra will turn over due to dense environments such as methods such as mixed free absorption and synchrotron self-absorption, such as in the ODA 1998 review of such topics. And at high redshift, these would appear to be shifted from, say, hundreds or maybe even gigahertz down to tens of megahertz or less. So peaked in sort of these tens of megahertz in frequency. And so with GLEAM, which probed bands from about 70 megahertz to 230 megahertz, some selection was applied on the spectral steepness and then curvature within GLEAM to try and select for these types of sources. And in the bottom right there, pardon me. Bottom right there, this is from one of the initial pilot samples, whereby this source was selected to have a possible turnover from GLEAM, which is the inset of these sort of 20 subbands over here. This isn't quite enough. We don't actually have any confirmations just from a hint alone. So we have to figure out how do we actually find the redshifts of such objects. And so typically, we're very heavily reliant on getting redshifts from millimeter infrared and optical spectra. For example, there was an ALMA campaign, which I worked a little bit on, which yielded redshifts for 4 sources, one from being already from the pilot, and 3 in the extended sample, which I worked with. And that's looking at molecular carbon monoxide emission lines and also neutral carbon lines to try and get redshifts. And this is one such source from the pilot sample. And then one of the ones which I worked on, which ended up being in a protocluster at redshift 3.8, which was very overdense for typical source populations. And then on the other side of things, going to shorter wavelengths, this is one that Nick had worked on, which is confirmed from HST observations covering more so the near-infrared spectra, also from the pilot sample. But as I've learned over the last 2 years, it's very hard to try and get time on such oversubscribed instruments such as ALMA, HST, JOST, etc. And so at this point, I've given up. There's not enough time left in my PhD. So I'm going to go back to radio wavelengths instead, and I'm going to have a look at what I can do at longer wavelengths. So how low can we go? The answer is with LOFAR, specifically the low band antenna. So from 2020, there were 7 nights of 3 observations that were taken under a project that was led by Jess. And this was with the low band antenna spanning 34 to 66 megahertz, which is quite complementary to GLEAM, which goes from 70 megahertz upwards. And for this, we had 3 beams, 1 for the calibrator source and 2 for the target fields around the pilot high redshift radio galaxies, which were already confirmed by that point. And then we look for if we can see any turnovers in SEDs. But first, a very important question, can we even reduce the data to get this result? And this is where I had a bit of a painful journey over in the internship, whereby I was trying to reduce data at even lower frequencies than I had ever done before. So this under George Heald, and it made a huge use of Doug, which is courtesy of credits that were obtained by Stephen. And so with that, I set up the pipeline for low-fi LBA, which is developed by Astron, and it's in active development for the LOLS survey in particular, which is the low-fi LBA Sky survey. And so most things were already in place to sort of reduce the low frequency data. But there's a catch. For these target observations, they were very much equatorial, being shared in shared skies by MWA and LOFAR. And this is a lot lower than what typically the LOFAR teams work with. And so I think LOLS will cover this maybe eventually, but so far they're still stuck on working with the more zenith pointings, which is what they've developed the pipeline around. So I had to adapt to the pipeline a little bit to work for targets at low elevation, which is dealing with stuff like elongated beams, differing ionospheric effects, and a bit more. So in the kind of short summary, the way the pipeline works is generally sort of, basic common steps that most pipelines will work with at low frequencies. You get your calibrator source and get amplitude solutions from that. Then we move into direction-independent effect calibration and correction, whereby we get the text solutions and scalar phase solutions calibrated. The pipeline works on several different patches of flux within the field of view, so it's not quite direction independent. There is a little bit of direction dependentness there, but it's very few patches whereby you get text solutions to try and get nice corrections against the ionosphere for. And then we move to sort of the more heavily direction-dependent calibration, where we make up a lot of different facets. And we do sometimes amplitude, but mostly phase self-calibration cycles in those facets for some compact bright sources. And then hopefully in the end, we get some nice wide field images with, additionally, this is quite important, the 8 times 4 megahertz subbands. So we get spectral information for these low frequencies to try and find the turnovers. So here's an interesting example of going from the direction-independent corrected image to then 2 cycles of the direction-dependent corrections. And it cleans up quite nicely. So another bonus of having the subbands is that you can make pretty false color images as well. So here I've just done something in Carter with the multicolor blending from one of the more recent versions. I think Jordan will be happy to see this being used. And so by eye, you can even see some sources which have sharp turnovers have bluer colors as well, just at a glance. That's quite neat, but let's actually get some modeling them. So this is still preliminary at this stage, because I kind of whipped it up in the last couple of weeks or so. I combined the subbands from the low band antenna with the subbands from Gleam. I attempt to fit several different models to the spectra that come out of these, like a single power law, double power law, and then a couple which have the curved component at the low end, which is from either free absorption and synchrotron self-absorption mixed plasma interacting with the emitting region, or for example, free absorbing surrounding screen from the source. So I fit all these, I select the best via Akaike information criterion, and I find that quite a lot of them actually have turnovers or significant flattening at the low frequencies, such as with this one up here, which is selected to have the free and synchrotron self-absorption model. And that's kind of shown in this little inset here. But you still get lots of steep spectrum sources as well that aren't turning over. So for the most part, we are fairly convinced that the fluxes are quite reliable. And they can line up quite nicely in Gleam in these examples, although I'm not going to show you the ugly ones. And the contours that are overlaid on these LBA images are from the MIDAS survey, courtesy of Sean Patterson, another one of Nick's PhD students. So what we really hope to see with these model fits is that we can combine them with size constraints as well. If we can do this, we can actually compare sources with the O'Dea relation that I kind of mentioned before, which is the relation between intrinsic turnover and linear size. So it's a fairly strong relation from O'Dea's work. And if we can get really solid size constraints, either from, say, international LOFAR or VLBI, then we can start to sort of figure out what sources with their observed turnovers and angular sizes could look like if they had a certain redshift to get intrinsic turnovers and then linear sizes. And maybe make a redshift track to then get a redshift prior on such sources where we don't detect the host galaxy and therefore can't get easy redshifts from them. So this is sort of looking at how can we estimate redshifts from radio alone and not rely on millimeter infrared and optical as much as I just found that I couldn't get any data for those telescopes. So one such tool we could use is interplanetary scintillation, which is the scintillation of compact sources from the solar wind. And from work with John, Rajan, Elaine, and others, the MWA IPS papers, Rajan created this thing called the Normalized Scintillation Index, which tells you a little bit of a pseudo size constraint for sources that are unresolved to MWA. So for sources unresolved to MWA, which is at the time of the IPS surveys, sources less than 110 arcseconds, the NSI tells you about the spatial scales of fluxes down to 0.3 arcseconds, which is the Fresnel scale at 162 megahertz. That seems to be quite a powerful tool, but you need to be able to calibrate it in order to use it for actual proper sizes. And so for one example, we have one of the pilot sources with VLBI, and we see that it has an NSI of about a half, which I'm not going to explain the huge details, but essentially means that it's indicative of two components at 162 megahertz being marginally extended beyond the Fresnel scale, but also separated by more than Fresnel scale, which seems to be suggested by the a bit higher frequency observations here, the two red blobs. And so that's from another one of Nick's follow-ups of this source. And this gets us a direct size, which we can then compare to the NSI a little bit. And then in the future, if we do have examples such as this, where we have size constraints and turnovers that we see quite clearly, we can then see how they sit on the O'Day relation here. This is with much broader band SEDs, so these two sources have had lots of follow-up over time, from here in the LBA down to 30-ish megahertz, all the way up to 100 gigahertz with ALMA. And so this is just simple triple power law fits rather than the curved ones that I showed before. But essentially, the turnovers are fairly well detected, and we get our rest frame turnovers from that, and then you can put them on the O'Day relation here, with an actual size constraint from 0917 in the red. But for 0856, we don't have VLBI, so we just have a limit there. And so to summarize, I've worked with both the Gleam survey subbands plus the newly reduced LOFAR LBA subbands to try and get these low frequency features validated that were initially selected for. So that's the big thing, that they were selected for these turnovers. We saw the turnovers, all good. But there's also many other sources in the LOFAR field of view, also rich in spectral information. And so we would hope to be able to look at these as well, although it's a little bit beyond the scope of my current plans at the moment, but hopefully I'll get there in the end. It also makes you wonder if maybe future wide field VLBI campaigns, or maybe if you have more access to LOFAR, the International LOFAR Telescope, to get better size constraints on sources, so you can actually sort of tie it in with the IPS if possible a little bit, or just skip it and go to direct size measurements and go to direct size measurements, and maybe leverage the strengths of wide field observations of the radio, such as with wide field VLBI or with such as LOFAR International Telescope, to sort of get this constraint on redshift priors from the radio alone, rather than relying on optical and infrared deep fields, which obviously a lot of these radio sources are not well populated in deep fields since they're over the whole sky. We've also learned a lot of lessons for reducing at less than 100 megahertz with the pipeline flow LOFAR LBA, and Doug has helped a lot in getting the job done. Thank you. Any questions?
Thank you, Ajay. We can take questions from the room first.
I guess you'd kill two birds with one stone if you did effective wide field VLBI at very low frequencies.
That is true. With what instrument would you suggest?
Just pointing it out.
A new one, perhaps? Your next big project? I think the landscape of how much land there is in Australia would be quite beneficial to that. So we will have lambda eventually in the future, although that's not quite to the frequencies low enough that you can probe, such as with LOFAR LBA. So you might not get all the turnovers, but you'd certainly get a bit better than just Gleam alone, for example. Yeah.
Any more questions? Yeah, we have time for more questions. Okay.
Hi, Jay. Very interesting. Yeah. So just to comment on the IPS, that we can sort of we can sort of run a source image or a source model through some weak scintillation physics and come up with an NSI. So if that's useful, we can sort of try and see how that all works. I have sort of just about been able to pull the O'Day relationship out of the IPS data alone, not the exact numbers of it, but you certainly do see a sort of statistically significant decrease in the NSI as you go to lower peaks. So that's how, using a very, very simple model where you put all of the sources at a fixed redshift, but it does seem to give you roughly the right relationship, which is good.
With the modeling, is that also related to Sophie Young's work, or is that separate?
No, totally separate from Sophie Young's work, but exactly that kind of thing. Yeah, I think Sophie's actually just used Rajan's relationship. So on my to-do list is to contact her and talk about maybe taking a next step. But yeah, thanks for bringing that up. I've forgotten about that.
So the physics behind the O'Day relation makes the assumption that it's synchrotron self-absorption. But there's pretty good evidence that these turnovers might be free absorption. How does that affect what you're doing?
Yeah, well, I'm not at the moment. I'm not differentiating whether the turnover and hence the turnover frequency is due to synchrotron self-absorption or free absorption. So I'm not actually taking that into account at all. I'm just saying, here's my turnover. Let me try and roll with it for now. I'm still very preliminary at this stage. So further down the line, I think I would have to think about that a bit more carefully. But
did the O'Day relation go down to these low frequencies?
The answer is no.
No, because it's down to only, I think, 100 megahertz at most, I think.
Yeah, plenty of them, plenty of the objects in that paper and other papers have no redshift. So yes, that's possible. But you can get the same relationship from free absorption. So it doesn't have to be synchrotron self-absorption to manufacture that relationship.
Or even a mixture of both.
It's also a relationship on a log-log plot that looks really good. I'll just say that as well.
Thanks, Stephen.
We have one last question.
It's more a comment to answer Ron's question. Whether it's synchrotron self-absorption or free, that would be the information about the host galaxy would help disentangle that. If you had VLBI to get the position of the radio source relative to the host galaxy, if it's free, then it's got to be fairly local ionized gas in the galaxy. And you could do the calculations for synchrotron or free and see which is more feasible.
Yeah. On that note, I didn't mention it, but for this source with the VLBI, the green here is an extended ionized gas emission from Nick's work. And the best model for this source is actually the free absorbing surrounding screen, which actually lines up very well with these observations. So that's quite satisfactory as well.
Thank you. Oh, all right.
Oh.
It's one of my favorite topics, and you talk as causing things to be paged back into memory. One thing you might consider, a really good tiebreaker between synchrotron self-absorption and free absorption is to look at the spectral variability of a given object over time. And there are quite different theoretical expectations about the variability above the peak and below the peak in both scenarios. So if you've got the ability to look at your objects over time, especially at really low frequencies where if it's free absorption, you're very sensitive to the absorbing screen. That could be something for you to consider. And Kat endorses my statement.
I think that might be best done with maybe epochs of lots and lows rather than with these low elevations.
Just one comment from the audience from Cat Ross saying, took the words right out of my mouth, Stephen.
Yep.
Yep. And I was actually joking when I said when we have more time to question. But thank you for asking all the questions and thank you so much, AJ.
Yep.
Yep. So then next one is going to be from Christian Di Pietrantonio. Yeah, I practiced it well. And yeah, it's going to be on the high time resolution imaging for fast radio burst. Yeah.
Thank you. Hi, everyone. Let me introduce you to Blink. Blink is a GPU-accelerated fast radio burst search pipeline for the MWA I've been developing over the past couple of years as part of my PhD. My name is Christian Di Pietrantonio, and I work for the POSI Supercomputing Research Center here in Perth. And also, I'm pursuing a part-time PhD at Kyra. I started with Marcin Sokolowski, I've been working with ever since, and a whole bunch of very competent people who are helping me on this task. So let's get started. In a nutshell, what I'm doing is, the goal of the project is to look for low-frequency fast radio bursts within MWA high time and frequency resolution data stored at the POSI Center archive. I identified 3 phases of the project. Phase 1 essentially is developing the actual code to run the search. Phase 2 is to run a small pilot search just with the goal of understanding the behavior of the code, whether it's good enough or there needs to be some more refinement, understanding the science parameter, technical parameter. And then phase 3 is to unleash the software on the VCS archive. In particular, we are targeting, at least to start with, the smart survey. That's the whole idea. Let's start with FRBs. So FRBs are very bright, usually 10 to the 39 erg, but also very short in duration radio transients, the millisecond scale, whose origin is yet to be identified unequivocally. They have been identified and detected quite a few now at higher frequencies, mainly by CHIME and ASCAP and other radio telescopes. But only one low-frequency burst at the frequency of MWA has been detected and confirmed so far by LOFAR, down to 110 megahertz. They seem to be randomly distributed across the sky and in time, so predicting when the next one is going to be, apart from, in general, it's hard, but sometimes there are repeaters now. They've been identified as a repeater. And so sometimes you get lucky and you can point to the location and you see the burst repeating, and that's how I identified this particular burst at low frequency. So this is a targeted search for a non-fast radio burst repeating at higher frequencies. If you were to look for FRBs with a NWA in a blind search, meaning that you don't know where they could happen, so you're looking the whole sky, keep looking until you find them, essentially. If you were to perform such a search with the NWA, a typical configuration is shown in the table 1 here. So you have to consider with a central frequency of 150 megahertz and a chosen dispersive delay, a representative one of 600 parsecs per cubic centimeter, you're looking at around 40 seconds of dispersive delay. And with the large field of view and angular resolution of the NWA, you get a quite large number of images being generated and to be considered at any given time during the dispersion. So we are talking about around 600,000 of images, or equivalently 600 gigabytes, 600,000 gigabytes of data to consider. So it's a challenging problem on the computational side, but also on the science side, because FRBs suffer from accentuated signal propagation effects at low frequencies, such as dispersive delay, scattering, scintillation. Nonetheless, it's important to have, if we could detect them at low frequency, or have more detections at low frequencies. They would complement information provided by higher frequency detection, and they would allow us to study progenitors. So what is the astronomical object causing the magnetar systems of neutron stars, their emission mechanisms. So what is the process causing FRBs within these progenitors? the energy emitted maybe as a function of frequency and emission structure, and also interesting is the local environment FRB. So what's the environment surrounding the source of the FRB? They also function as a cosmological probe as well, giving us information on the path they are traversing towards us. There have been previous searches for FRBs with MWA, starting, I guess, in 2015 with Stephen Tingay, and then the most recent one published is an image-based search by Ian Kemp. No FRB has been found so far with the MWA. There could be multiple reasons for that. There are several techniques adopted here. Some of them are blind searches, others are targeted ones. And multiple reasons could be because of the non-detection. But what we come to think now is that there were limited availability, there were technical limitations, also data limitation in terms of time and frequency resolutions adopted, and also the total number of hours adopted. Essentially, not enough time and frequency resolution, not enough hours observed, possibly one of the reasons. So what we want to do is to change that. With Blink, we want to target this, the smart survey and also beyond at a high time and frequency resolution. So we want to work with the VCS high time resolution data. Smart survey was designed by Ramesh Bhatt to perform sensitive searches for pulsars and fast transients in the southern sky. So the observations are centered around 150 megahertz, bandwidth of 30 megahertz, and a staggering field of view of 610 square degrees. They collect a total of 100 hours observing time, or equivalently smart observe half of the sky for 1.5 hours, for a total of 4 petabytes of voltage data. So one could argue that 100 hours is not enough, but it's what we have at the moment, and maybe even more VCS data we could collect later on, but it's a start, especially at the high time and frequency resolution. One of the two things we started looking at, the two most, I guess, important parameters when you are planning for a search is to understand your data set and what it can actually give you in terms of sensitivity and the limit influence. This information essentially tells you, okay, what is the faintest FRBs you could detect if you looked at the data with a certain technique and time resolution. For a representative using an imaging technique with a 20 millisecond integration time, you're looking at 0.5 Jansky sensitivity theoretically, and a limit influence of 100 Jansky millisecond. That will mean, for instance, if the FRB detected by LOFAR had happened in the southern sky where the MWA was observing the sky to collect smart, we would have been under a lot of conditions, and we would have been able to detect the brightest pulses. Using those numbers, you can also do a rough estimation of how many FRBs we can expect to find in the smart survey. What we do is we take the measured FRB rate at higher frequency by other telescopes, and we then scale down to the smart frequencies, and using a certain equation that is a function of spectral index and effluence. So normally, what has been observed is that you have a negative alpha, a negative spectral index, but that value is kind of cancels out with accentuated propagation effects, one could argue. So a real, let's say, a more conservative and also maybe representative estimate is if we choose alpha equals 0. So we have a greater than 0, but less than 1 number of FRBs, but let's say I'm feeling lucky. Move on. Also, one thing I'm looking at is, okay, we have to choose the parameters such as integration time and bandwidth required, and you can see that relation between integration time and bandwidth required. We have that the finer the integration time, the finer the bandwidth required, but also the bandwidth also depends on the DM space you're searching for. The higher the DM, the finer the bandwidth required to look for FRBs. And the VCS data, at least I'm currently looking at the old ones, have a limitation 10 kilohertz, has been cited before. So that tells us, for instance, is that in looking at 10 millisecond resolution, for instance, you start losing, you have diminishing returns because the VCS data cannot give you a finer bandwidth, finer than 10 kilohertz. Yeah. Going on, the computational technique is that we have, the most FRBs have been detected with beamforming technique. However, when you have a large field of view, so with the MWA, as the number of pixels increases, or beams increases, beamforming becomes prohibitively expensive. That's why we move to imaging, but imaging is more efficient than beamforming, but still expensive overall, and also especially in terms of the data rate it produces. When we need to produce a high number of images per second of observation, data volumes goes up orders of magnitude as you move through the imaging process. To tackle that very quickly, I implemented the imaging, an imaging pipeline that runs, an FRB search pipeline that runs entirely on GPU. So we read voltages in on the GPU memory, and then from voltages to images, we keep everything on a GPU memory at all time. The computation stays there, and we avoid intermediate I/O steps that were happening with the classical imaging pipeline, and that was adding with the fact that you're using GPUs that offers a much higher throughput and so many more operations per second than a CPU with a much higher energy efficiency. We were able to get great results. At this point, we also implemented the dispersion and time series. At this point, we are stored in CPU memory just as a buffer overflow because we were saturating the GPU memory at that point. And we are planning to run this on Cetonics. So I'll skip the implementation details. If you're interested, come to me. But let's go to the quick results. First results. I tested the pipeline on a very bright pulsar to begin with, the B0950 pulsar, and I imaged the observation at 20 millisecond and 40 kilohertz time and frequency resolutions, creating images of 1200 by 1200 pixels. The process produces around 38,000 images per second of observation. It's nice to see that actually we could image the B0950 pulsar, so it's an easy load EM1 just to test that the software produces correct images. We manually extrapolated the time series as well, and the peaks are there. The reason we did the whole thing is because we want to go faster than traditional pipeline that actually Sosmita just described. If we were to use Sosmita's pipeline to produce the 20 millisecond and 40 kilohertz images, or 38,000 images per second observation, we project a time of 14 days based on the the execution time, based on the progress of the pipeline executed under the 24 hours world time limit on Garavarla. Our pipeline does the same job in 5 minutes, and of those 5 minutes, 80% is writing down the images to disk, an operation that is not required if we run the pipeline in FRB search mode. The first results of the imaging up until creating images are being published in 2 papers. The first one is by Marcin. Marcin designed the initial GPU imager doing the FRB, doing the gridding and FFT. I enhanced that imager, made it more performance, and then I implement the rest of the pipeline correlation, corrections, and etc. Now we have tons of images. What we do with them? I said that we cannot keep 40 seconds of worth of images in memory. We don't do that. What we do is that we image a second at a time. We do a partial dispersion on those images, and then we throw them away and compute the next second. We actually divide the dynamic spectra over time and frequency. It's a new algorithm, so it's a new implementation I've come up with, and it's going to be the subject of my second publication. The result of this is time series that then you can look for detections. I ran on the same B0950 observation, the whole pipeline, the FRB search pipeline, looking specifically for this as a test, the exact same DM, just to see whether we could actually find same pulses. And indeed, in what I call the detection map, you see the candidates plotted as a function of their position in the field of view or in the image as a pixel, and then the dot size is the flux density. And we do indeed find the pulse of the B0950. More challenging test is the crab pulsar that has a higher DM, around 57 in this case. Again, I created the image just to see where the Crab Nebula was, and then I ran the pipeline in FRB search mode, specifying this time a range of DM from, I know the DM of the pulsar is 57, so I specified a DM of between 50 and 60. And you can see we have a big dot up there where the Crab Nebula is. And the color of the dot in this case is it's a different DM. You can see the gray dot corresponds to DM of 57, which is the closest to the actual DM of the pulsar, yeah. For each detection, I also save the portion of the time series that triggered the detection. So you can see that there are 2 giant pulses there. Some numbers here. So 10 seconds of observation, we were very lucky to find in the first few seconds. 20 milliseconds, 40 kilohertz resolution. Again, 1024 by 1024 image size. 10 DM trials, all run in memory, no I/O, just except for reading the voltages in. We start with 75 gigabytes of voltage data, and we produce throughout the process 1.6 terabytes worth of images. We compute 5.2 billion sweeps of the dispersion trial over these images. And we took 12 minutes compute time on our fully utilized GPU nodes, so 8 GPUs working together to do that. Now, I felt very happy to find these results, but Marcin said, okay, could be noise, could be RFI, .p, could be everything. So he really wanted to see the dynamic spectra, and he went on and created the dynamic spectra and did. Despite the fact that he recently saw 100,000 of them, when he saw this one, he got also very excited. So Blink started as a project in 2020, part of the POSI Center for Extreme Scale Readiness. Marcin submitted a project and then became my PhD project, and it is a short the development timeline, and we are very close now to actually then start some real search, and I'm very much looking forward to it. So yeah, we are finalizing the software, running this, smashing a few observations, as Marcin says, working out the parameters, finalizing some implementations, and we plan to start a real search maybe later this year, early next year, and then start with Smart maybe in the second half of the next year, conservative estimates. We also have we're going to have summer interns working on the imaging part of the software, trying to improve performance or studying, see whether we can improve something else. So it's becoming more than more than one PhD project could be useful for many people to learn how to do coding and to do science. It's a good also playground for people to gain the skill needed for radio astronomy, especially in the future. Thank you very much.
Thank you, Christian. We can have a couple of questions from the room.
Thank you. Very interesting talk. One question: when you say that on your 5-minute runtime, you have 80% for I/O, right? When you say that when you compare the performance of Blink compared to WS Clean, you have 80% of your runtime, which is I/O, right? What storage do you use behind? Are you using local NVMe or Lustre, or what do you do?
Yeah, that's a very good question. That benchmark is run on a local NVMe on the node. So I ran the benchmark on a second of observation. So the data produced was enough to be stored in the 3.5 terabytes NVMe on the GPU nodes. So just to avoid performance issues with the distributed file system. So both of the software were run on the same conditions, as stable as possible.
And for now, you are single node. You don't have any MPI or distributed version of it?
It's multi-GPU, but no MPI. If I can avoid communication, I'm happy. But yeah, the good thing of Cetonix node is that it has 8 GPUs, and they're enough to process the observation. If you want, parallelization of multiple nodes will be achieved just processing multiple observations on multiple nodes.
Okay, thank you.
Any other quick question? Okay, any
Hi, Christian. That was such a good talk. My question might be a little bit naive because I am not in this space. All of the candidates that you were showing, so when you had like the plot of like the position of all the candidates, the size of the dot was the brightness of it. Are all of the rest real candidates or?
Oh well, that's that's a good point. With this type of this pipeline is very fast and it's it's searching on all the big chunk of the field of view, so it's going to generate a lot of candidates. So you cannot flip presto plots like with the keyboard like you used to. You need a new methodology to sort and score candidates and then see the most promising one. In this case, I said just this was one of the first ones that I ran, so we're a very low threshold just to make sure I got it right. And so that's mostly noise. But as I go through, there are a few of them that I'm like, looks interesting. I need to further check it out. I guess another point I want to make is that we do offline search now, so we can do the type of thing that okay, let's look at the dynamic spectrum there. But when you run it on, if you ever want to run it, maybe real time, you won't be able to save the dynamic spectrum of every candidate. It's going to be a lot of space. So it needs some thinking. So also to think about how do you judge whether it's a real thing or not. You might have limited information. So it's something to think about.
Awesome. Thank you.
So I had another question on that real-time aspect. You have to calibrate the data before you can do this. So how are you doing real-time calibration?
Yeah, that's a good question. So we use pre-computed calibration, so they are not as extremely accurate as if you have to do some very detailed image or very precise image of the sky. We're using these dirty images as well, so we turn off any type of computation that is required to make the image as high fidelity as possible. We don't need that because FRBs and some transient are very bright. We hope to see for them. We have seen them to be bright enough that even some distortion because of not a precise calibration shouldn't affect the detection too much. But we use pre-computed calibration solutions.
So that would be the geometry. I'm not sure what you mean by Where's this information coming from?
They are pre-compute. I think preceding talk by Greg said that they compute calibration solutions before and after an observation. So that you have a calibration observation, then they compute these calibration solutions, and then it comes to me as a data product that I use. I'm not familiar with the whole process of creating calibration solutions, but I just use them as a product that comes to me.
All right, so thank you for the questions, and thank you, Christian. And catch Christian when you get time. Okay. No, that's we just got that, but let me just grab that and try. This is the one? Oh, no, sorry. Yeah. This one? Thank you. So the next topic is from Richard Dodson.
I don't get the notes. I can do it without, but anyway.
Oh, all right. Thank you.
Okay, I'm Richard Dodson. I interrupted my introduction. Thanks for the opportunity to talk. I wanted to tell you all about something we've been doing over in DIA for completely different reasons, but I think it's got a lot of application to MWA. And the specific title here was because I was hearing about how the archive was being emptied, and I thought we had an alternative here. We could delete the data rather than, compress the data rather than delete it. The outline, my motivation is really coming from the deep spectral line analysis that I'm part of the DINGO team on ASCAP, and the SKA and the ASCAP model for multi-epoch observations is you make the daily image and you stack those, and I hate that, more than I should really. IO is And in addition, I/O is a huge performance limit, so we're always aware of that issue. And storage is one of the largest cost drivers for the SKA. So I'm hoping that we can save a lot of money, and then I'll get 1% of the money back that I've saved them. So that's the motivation. The insights were that stacking images is just wrong. I mean, it's just they're mathematically wrong, it's scientifically wrong, it's morally wrong. We shouldn't be doing it. I hate it. And of course, also we all know that the radio interferometric data that we get is completely noise dominated. So we know we can be much less precise than we are being. The tools I'm using are from Oak Ridge National Laboratory, people we've been collaborating with for a decade or more. And they have this parallel I/O tool called ADIOS, and they've recently added a compression unit into that ADIOS library. So because we're working with them on ADIOS, we also had the ability to pick up on MGAD. And I'm comparing, well, not in this talk, but I did compare it to Disco. The data we used OS for simulations, but now I'm mainly looking at real data. Simulations are useful, but now it's mainly real data. So where can you compress data? Well, first of all, we've got these digital voltages, which have got a quantization level, and if you could improve that quantization level, perhaps you can improve that. That is really driven for us by the EHT, where they have a phenomenal data rate. I mean, it's frightening, 256 gigabits per second. I don't know how, they don't know how they're going to handle it, so I certainly don't. Secondly, what I'm going to talk about here is the output of the correlators, how we can compress the output of the correlators where you've now working with visibilities. The original driver was this Dingo work where we're forming an intermediate product on the grids and we're compressing that. The difference between those two is one is lossy compression and this one on the grids is lossless compression. And finally, something I'm doing nothing with, but we've passed this back to the Oak Ridge people to look at, is the radio sky is largely empty. So these image cubes can be heavily compressed. So that's a fairly standard compression problem, and they're working on that. I wanted to say very quickly the difference between these two methods, Disco and MGAD. MGAD is what they call a multi-grid method, and Disco is just bit truncation. I'm sorry, let me go back. So bit truncation, you just use less bits. Couldn't be simpler. You use half the number of bits, you've taken half the space on disk. Whereas multi-grid methods, you try to detrend the data before you do that. You do the same bit reduction, but you detrend the data first. And so if it's noise only, there's no trend, so they end up pretty similar results. But if you've got a signal with a trend, here I've got a linear growth with a sinusoid and noise, and you can see that the bit truncation would, in blue, produces very large residuals, whereas the bit reduction in the truncation in a multi-grid-like method has much smaller residuals. So this is why MGAD has the potential to be much bigger, much better than Disco. But in addition, because we're really noise dominated, you're selecting by error level. You're not saying, I'm going to reduce my data volume by half. So because I have a bit level truncation, I'm selecting to an error level. I'm going to allow an error to 1/10 of the system temperature, 1/100th of the system temperature. In addition, it's got all these other options, which is mainly the parallel I/O provided by ADIOS. And in addition, ASCAPsoft has all of this compiled in a slightly off main branch that we've been working on with Dingo. So Dingo, the original focus, this is the default approach for both SKA and ASCAP. You make a daily image and you stack those images. You horrible person. The traditional approach is you keep all the data. Who cares about the cost? And you process the data in one massive joint deconvolution. That's what we did with Chili's, where we have 1,000 hours of VLA time and we just process it all together. Very slow. And you need massive amounts of disk space. So we propose this intermediate where every day you made a grid, and that's what you store. You don't make the image. You do make the image, but it's not relevant. You make the grid, and that's what you store, and that's what you stack. And once you've stacked in the visibility domain, which is where you should be doing it, you do that final imaging. Now, advantages. With imaging stacking, you can do no further deconvolution. You've just stuck at your daily deconvolution limit. With the traditional, you can do major cycles because you've got the original data. But with the grid stacking, you can only do minor cycles. So we actually do a major cycle, a daily major cycle before we do the grid stacking. So we keep a model for every day, a grid for every day, stack all of those, and then we can do an additional minor cycle, and that's working very well. This is a plot that's a bit too complicated to discuss, to break it down in detail. White is good, green is bad. You can see, and we're comparing visibility, traditional methods versus grid stacking, and at the bottom, traditional methods versus image stacking. And you can see that we're getting fairly good comparison with grid stacking, and it's going badly wrong with image stacking, particularly when you start to apply weights. And that's kind of obvious if you think about it, because you're doing in the traditional case, and doing it right, you're doing the mean of the sum, and the other one, you're doing means of sums. So we know that's wrong. Here it is on real data. So that was simulations from Christoph's thesis. I forgot to mention his name. All three methods of producing the galaxy is looking pretty much similar. But if you start to look at the details around the edges, the traditional, you see this wispy, probably high velocity cloud off the edge of it. We get recovering the same with grid stacking, but with the image stacking, that is just getting completely washed out. And it's just diverging. The spectrums all look pretty much the same. Now, turning to the compression, which is after all the title of the talk, with these grids, they're largely zeros. So you can compress them in a lossless fashion very efficiently. But we've also explored the lossy compression. So lossless is on the far left, and then as you allow greater and greater errors in your compression, you can have more and more compression. So we're going from a factor of 7 with lossless up to 30 or so with 5 minutes. Okay, I'm not going fast enough. So we're sticking with lossless for Dingo, even though the lossy looks promising. And in this particular case, we've also proven that it was, with this 7-fold reduction in volume, we got a 7-fold reduction in processing time. So we're really showing that it is IO dominated. And so that's great. Now the visibility, raw visibility, which is really the MWA case, I think the crucial point is the system temperatures are set by our first stage amplifier noise temperature. And that, if you've designed it right, that is your limit to sensitivity. And compression can just be thought of as additional additive noise. As long as your additive noise is less than the system temperature, less than that noise from the first stage amplifier, you have not negatively affected your data. So we can, with this justification, we can allow for lossy compression of the visibility data. Because I've got my notes, I'm not really sure what's coming up next. Okay, so looked at MWA data, just tried it. Here I am at the top, along the x-axis, I'm allowing for greater and greater errors as we go further and further to the right. And vertically is the compression ratio. So it starts low, order of a few with very tight error bounds. But as I increase those error bounds, I can go for, I can compress greater and greater amounts, up to 100-fold at levels that are really too extreme. But if I limit myself to a compression error bound of 1/10 of the system temperature, I'm getting a 10-fold compression of that data. And then when I look at those impacts on the images, that same sort of 10-fold compression ratio is increasing the image RMS by 1/10 of sigma, or the maximum error by 1/10. I must have got those 1,000th of sigma, and the maximum error is 1/10 of sigma. So we really are not, even though we're compressing it by a factor of 10, we're not altering this data significantly. And I don't know if I mentioned that this is all Gleam data that I just happen to have sitting around. Now, I don't really like using the RMS. It seems a very, very popular metric, but the RMS doesn't capture a lot of effects. So we've looked at a lot of other metrics, most of which I won't talk about. But perhaps a useful one to think of is the maximum error rather than the average error. What is your worst error? So I'm going to kind of focus on the maximum error from now on. But it's recently suggested we should look at the closure quantities as well. I haven't done anything with that. It's just an idea made last week. So how does that compress? How does that impact the image? The dotted lines are the image RMS. And as I increase the error bound, you can see that the error that I'm introducing to the image gets less and less and less. Now, this is the no deconvolution case. I'm avoiding clean. When I add clean in, I actually hit a limit. But this is a limit from cleaning. And this is this particular data set I could achieve with 64 antennas in a complicated sky. I could achieve a dynamic range of about 1,000 to 1. If I had a simpler sky, I can get a higher dynamic range, and I can bring that limiting factor down. But currently, what I'm seeing is clean is the dominant source of error, and that's actually more important than these error bounds. So I could even go more aggressive with the error bound because I know clean is going to be a limit. Now I'm switching to plotting maximum, and I think I'll just pick out tests with the next generation images are going to be important here because the limits we're seeing is really more a discussion of the limitations of clean than anything else. Here are real solar data images. First one's the original, and then I do a 1%, introduce an error by 1% of sigma, I get a 10-fold compression. If I go to 10 times a tenth of sigma, I get 20-fold compression. At this point, I can see no difference in the images. After that, I can start to see the image degrading. When I get to 1 sigma, I've significantly degraded the image, but you're really getting great compression and no impact on the image. And that's re-enabling science because, first of all, we can keep the data for longer. Secondly, we can do joint deconvolution. We can keep the data and then do it processing all at once. And also, it's going to be so much faster. So the big problem to me is with these solar ones where I had to divide by, which one should divide by time and by frequency, you end up with a huge imaging budget. If you can speed that up by having smaller data sets, you'll be able to get through your data more quickly. And processing that takes too long never gets done. And the finances are not inconsiderable. Storage is very expensive. So by reducing the footprint and saving money on the storage, you can really help. And in this particular case, the MWA archive, we're offering as a service. We've got a project with ADAX. The idea is you as a user will have a Delugi graph. You put in the names of the observations you want to compress. You put in the limit that you want to compress to. It will go and process on your local computing and just give you that compressed net data set. So this is a project we've got with which is funded. Out of respect for time, I won't say anything about the future, just go straight to the conclusions. Dingo, I think we've got bedded in. We really have a solution now to achieve thermal limits with the 32,000 hours worth of data that Dingo has allocated. We've only demonstrated on the first 200, but it's working. So we think we have a method that is suitable for ASCAP and is suitable for SKA. Looking at the raw visibilities, again, we think we can compress things by, say, a factor of 10 with no appreciable impact on the images. And we're going to make that very usable, if that's not repetitive. And I'll stop there.
Thank you, Richard. So we can have a quick couple of questions.
Thanks for the talk, Richard. I was just wondering how much processing power or processing time or resources does it take to actually do the compression itself, or is that relatively
Good
inexpensive?
question. It doesn't seem significant. I can't. We've got a draft paper and it's in there and it's not significant, particularly if you're going to do massive imaging problems. And this was even how we did it. We were doing all this computing on the CPU, and it's really GPU-enabled code. So it should be even faster and have an even smaller input. But it is completely dominated by the fact we reduced the volume, and everything's sped up by that factor.
Awesome. Thanks.
Okay.
Thank you for the talk. Very, very interesting. Like you know, we have a similar effort in Switzerland too that try to do compression, especially for visibility dataset and like any form of radio astronomy data. We just started that pretty recently. It makes a lot of sense for everything that you have said, but also for data transfer, right? Because like in the SK, everything that need to be transferred sooner or later between the site and the SRCnet side will apply to pass through internet. And then like any compression we can get on that is benefic, of course. One question I had is, have you tried anything related to variable autoencoder or machine learning technique for like compression?
No machine learning at all.
No machine learning at all, okay.
So I have seen your proposal, as I said earlier, and that was a very interesting aspect to me. I would just like to make a point. One of the things in DIA, the Data Intensive Astronomy group that I'm part of, is we have the responsibility for designing the receiver nodes for the SKA. And whilst they have clearly said no, I think reality is going to come along and force them to use compression. And I think the ideal place to put this compression is in the receiver node. So as you're streaming off the correlator, you could just compress that on those receiver nodes and then pass compressed data all the way through the chain. There is no need to have it written to disk in compressed format and then read it back and uncompress it. Just keep it compressed, keep the memory I/O down, everything becomes so much easier.
Yeah, I do agree.
If you've got a tenfold compression.
I do agree. It's especially valid if you have GPU on this node currently. You can do much more.
All the machines they're buying should have GPUs, and they're not. That's another story.
All right. In the interest of time, we will move on.
I think there's one here from Ron.
One? Okay, we only have the one last one.
Just a simple question first. You've got a compression algorithm. When you want to use that data, do you have to have a reciprocal decompression?
Yes, you do. Yes,
everybody who uses this.
Yes, you do. Yes, you do. And that is also true for Disco, of course. But and we are having a lot of fun trying to get this MPI software to compile inside ASCAP soft, which is MPI, and keep all those MPI ranks, stopping fighting. Fortunately, it's not my problem, but it's not one that we're solving easily. But it can be done. But unfortunately, he lost his job, so we're trying to recover exactly what the necessary steps are. But getting that all compiled and playing nice is a non-trivial challenge, much more than it should be. But that's not my expertise.
Okay, and the second question, if I may, you pointed out that RMS is only one measure of the quality. You then went to peak difference, but I would think people would be more worried about biases. That is, how do you know all your flux densities aren't systematically biased after you've been through a compression algorithm?
Well, all those numbers I give are difference between the image made with compressed data and the image made with the original data. So a bias, a shift would still pop up in the maximum error and maybe even the RMS error.
If it was a small offset over a large area.
Well, the other thing I did was look at the 2-point correlation, and I think it would show up as a spike in the 2-point correlation at 0. But yes, that's an interesting, I hadn't thought of that particular dimension at all, but it would be picked up in the 2-point correlation. That was really looking for ripples left over through the compression, and none of those showed up.
All right. Okay. Thank you, Richard. is loading. Yeah, so the next talk is going to be on challenges and opportunities on wide field radio transient monitoring from Natasha Haliwaka.
Yeah, thanks, Marianne. Okay, there we go. Great. All right, thanks all. I have the unenviable last slot of the day, but I had teaching, so thanks for making time for me. So yes, I wanted to talk to you about one of the more recent use cases for the MWA, where we've been having a lot of success, and also go over a few of the challenges that we have in detecting rare classes of transient objects with this low frequency instrument. So since we're in a project meeting, I thought it was kind of a nice time to go back and look through all of our proposals and see whether transients was an early use case for the MWA. And so these are some of the earliest guaranteed times, so from MWA partners, proposals that were put in to use the telescope early on. And actually, about a third of these proposals are to do with transients and variables. This was seen and recognized early on as an exciting use case from pulsars to FRBs, ultra-cool dwarfs, and also just looking for things that we might not expect. So this was, we started off with great hopes and expectations, but it, of course, is all very, very challenging. And so while we are now at the level, I think Ramesh, is getting the SMART survey going really well. So we're finding pulsars. We've had some good limits on the detection prospects for FRBs. Christine Lynch did a great job with the ultra-cool dwarf project. We haven't maybe seen a complete bonanza of transients as we might have expected from these original proposals. However, we have discovered a new class of transients using this telescope. So this was not something that was originally in the proposed searches because we never expected to find anything like it. So in 2020, I was running an undergraduate project with Tyrone O'Doherty, who was, I'll talk a little bit more about the method that he was using, but we were searching through our data and looking for unexpected objects in our galaxy. And we found this very, very strange object, Glimex J1627, rest of telephone number, that produced a 45 Jansky pulse in the observation that we found it in. And I don't know about you, but I didn't enter my career in radio astronomy expecting to still find unknown 45 Jansky sources, right? You'd think that we had discovered all of those, but no, there are indeed still more things on heaven and earth than we had dreamed. So this source produces 30 to 60 second duration pulses, and you can see in that, I'd say it's an animation, but it's not an animation, that's just the real data in the middle there, where you can see the source coming in and disappearing, and it's brighter than everything else. So I think I have subtracted the sky model here, but I don't think it matters. This source is staggeringly bright. And you can see on the bottom left of the animation what that pulse looks like over time. So this was unexpected because pulsars are not supposed to spin this slowly. They're not supposed to produce pulses that last a minute and repeat every 20 minutes. And the source was also very linearly polarized. So we theorized perhaps it was some kind of magnetar or white dwarf. Now, this was a little lonely discovery for a little bit, but I guess perhaps the astronomy community has learned from the experience of FRBs, where one was discovered and then everyone ignored it for a bit, and then we went and found a whole bunch more. The discovery rate for these objects has been very rapid. There is a little bit of similarity with FRBs because retrospectively, when I was going through all the literature, it turns out that in 2004, Scott Hyman and collaborators saw a source that just produced 5 pulses separated by 77 minutes, and they never saw anything else like it ever again. So you can see there's a sort of 20-year gap here between that initial discovery. And the critical difference between then and now, they kept looking at that patch of sky, and occasionally they saw some weird bursts that may or may not have been the same object. But nowadays, we can scan enormous fields of view with these wide field SK precursors. And that has meant that after the publication of that source, many observatories around the world rapidly retooled and started looking for these sources. So we're seeing this explosion of discoveries, and you can see MWA in red there, doing the initial discovery work, and ASCAP really taking the lead because it has a lower, scattering has a lower effect on that higher frequency instrument. So I'm going to keep coming back to wide field because Ron's looking directly at me. I am obviously going to keep saying it, but he's a very strong proponent of wide field of view, and that is because it is how we discover transients. So to give you some context on these long period radio transients specifically, until the last month or two, this was a pretty sparsely populated diagram. But just, in this year, we've had so many papers published with so many exciting discoveries. And I've put them here in what is probably the wrong diagram to represent them, but it's a familiar diagram for many astronomers. This is the famous PP dot diagram, where the spin period of sources is represented on the x-axis, and the rate at which they're spinning down is on the y-axis. So all of the pulsars cluster together in that kind of colorful cloud. There are these objects, magnetars up here, which are very, very, very magnetic neutron stars, often seen by their X-ray emission, and our ever-growing collection of long-period transients out here. A big advance that we've made, and this has been partly done with the MWA and also LOFAR and CHIME, has been to associate some of these objects with optical counterparts. So those are in red, and we're pretty sure those are white dwarf pulsars, whereas the yellow objects are still, as far as we know, unassociated. So you can see this sort of vast area out here, which really wasn't explored compared to the traditional pulsar time domain. I've mentioned the physics a couple of times. I won't have time to go into all of the details in this short talk, but I just wanted to kind of spur your interest that these are really, really interesting objects. They're not just unexpected. They could lead to exciting advances in physics. So these magnetar objects up here are predicted to age down to the bottom right here, or to come out and then drop steeply, depending on the aging model that you use. And there was always postulated to be a population of ultra-long period magnetars. It's just that we thought these things would probably be radio quiet. So if some of these objects are ultra-long period magnetars, that could tell us about how neutron star magnetic fields evolve and decay. And there are models that predict that long period magnetars could produce fast radio bursts. So that becomes quite an exciting kind of thing to chase in that context. The other increasing, when we do make an optical association, what we're finding at the moment is that we're often finding a white dwarf in a binary with an M dwarf. This is really exciting. Literally, just in the last 8 months, we've finally got these optical associations. The thing is that the power emitted by the radio emission is much brighter than any of the objects that were selected by optical searches. So there's obviously a selection function there, but at the same time, all of the people who've been working on cataclysmic variables for years are completely puzzled by this very bright radio emission. So we're trying to work out right now about how the magnetic fields between these two kinds of objects might interact and drive these very, very, very luminous pulses, and whether they are emitted on the spin period of the white dwarf or the beat period between the systems. So my student Charnide, if he's in the room, he's just written a lovely paper on arXiv, and that's in review, that is looking at this kind of model. So this is exciting because the optical people, when they look for these systems, they can only find very, very, very quickly varying optical systems. And the idea that they could probe white dwarf spin periods of 20 minutes, hours, that's very exciting for them, because they would not normally be able to access those populations. They wouldn't be able to tell them apart from anything else. It also might tell you about magnetic field evolution in white dwarfs. So scientifically, these are great objects to chase, and everybody is getting on the wagon trying to find them. So we have our context. So how on earth did we miss all of these objects in the past, and how can we do better at finding them? These objects were almost all found via traditional time domain searches, which hopefully Christian covered a little bit in his talk, where you're looking on very, very short timescales, and sometimes you're doing folding, looking for periodic signals. But these have all been found in the image plane. So why is this the case? Well, I get to show a little bit of dirty laundry in talks like this. When we were following up one of our long period transients that we discovered with the MWA, we tried to use a traditional pulsar instrument to observe that source. I don't know if Danny's still around. Danny, still around? No? Okay. Well, Danny Price very kindly made the Breakthrough Listen backend available. And the Breakthrough Listen backend basically just records the raw signal. It doesn't attempt to do very much processing, because that's all done later downstream. And this horrible thing here is actually a pulse from our LPT. But you can see all of these gain variations, which are frequency dependent and on similar timescales. If you didn't know this pulse was here, you would not find it. If you use a pulsar backend, and these observations were taken by Ramesh with the Medusa backend, then the gain subtraction that removes those sorts of variations also completely eliminates the pulse. So pulsar search modes are just not really effective on these timescales if you employ any kind of gain subtraction. If you do, there are occasionally substructures within these sources, and this is a very, very, very small substructure, just 20 milliseconds across within one of our LPTs, and your pulsar modes can pick those up, but they tend to be a lot dimmer because they're only part of the overall emission. So interferometers are a great way of finding these things, and as I've said, this is J1627. We also have found sources with ASCAP, and we've also found unexpected sources. So I'd just like to highlight a paper by my student Flora, where we've found some eclipsing binary millisecond pulsars. So we're not seeing the millisecond pulsations, we're seeing the eclipsing of those pulsars by ablated material from the companion. And that leads to variation on long time scales, which we can pick up with interferometers. So it's very cool. So this is the transient phase space diagram. We have sort of a kind of luminosity here and a time scale here. And this whole area that's being opened up with LPTs is part of a general unexplored territory. So given you some scientific motivation for LPTs in particular, but who knows what else is out here waiting to be found. So I would love to go into all of the possible ways that we could find these things. I guess I just want to point out that traditionally people do source finding and then they associate each source with sources in other snapshots. You can also do differencing, which is how we found J1627, but I'll mainly talk about filtering. So a quick note on differencing in case people are thinking, oh, this was great, you found a transient, you should do this. This is taking two sets of calibrated visibilities taken some time apart that are LST locked. We built this into the GLEAM and GLEAM-X surveys so that we could do transient imaging very rapidly. And this was how we found 1627. This is the dirty image of the different visibilities, and this is a zoom on the source. The problem is the ionosphere was absolutely crippling, and that led to a lot of artifacts. And you can see in our plot of the number of sources with respect to their signal to noise that J1627 only just popped up as being significant. So I wouldn't particularly say go out there and do lots of visibility differencing. So what we're doing nowadays, or what we've done for the last couple of years, is run the galactic plane monitor. So we've been looking for LPTs by tracking the galactic plane, by pointing the instrument along it as it moves overhead. This has been very successful. I just need to find some time to write it up. I keep finding things. Perhaps of interest to this audience would be our pipeline, which is very, very bare bones, trying to make it as rapid as possible. We take a calibrated observation, we do some imaging. Now that we have a model column, we subtract it and we image each time step. And you can see the beautiful UV coverage of the MWA yields an almost noise-like cube with just essentially nothing in it. This makes filtering for transients really trivial. And so we get lots of, like a very low false positive rate, maybe we're looking at maybe 100 candidates and then we find something real, which is pretty good. And then we've found all sorts of things which we've written up in a bunch of papers. So this is, we kind of pioneered this, and then because we kept finding things, we have only just resubmitted the paper for review where we actually, did all the work. And so hopefully that paper will be out soon. So what are we doing nowadays? I have started a new program, the Nightly Investigation of Galactic and High Latitude Transients, or NIGHT. It's a sort of recursive acronym. And the goal here is we've found 3 LPTs along the galactic plane. That was very cool. But it's very helpful to have optical associations, right? That's where, you can really do some extra physics. You can't really do that in the galactic plane. You find things, but then it's very hard to associate them. Also, if you want to find bright and rare things, you are better off scanning a lot of sky. And so with this program, the main goal is to avoid really bright sources like Centaurus A and Hercules A, any kind of fields that we wouldn't ever be able to detect anything in anyway, and just cover as much sky as possible. So we've been granted very generously 1,000 hours until the end of this semester with a sort of ramping up of observations as we get a hold of the processing. So this is very exciting. Now, why is this relevant in our current era? Well, I went to Görlitz earlier this year and gave a presentation about how we could do fabulous things with the SKA. In theory, AA star would have the capacity to monitor the entire galactic plane in subarrayed, substationed pointings and do 10 times better than the MWA in terms of sensitivity, which actually isn't as much as you might hope. But there's a big problem with this beautiful view, which is that the imaging mode that we require in order to find these objects, this was information revealed to me after I'd given my presentation at the SKA conference, won't be available until 2032. And indeed, even pointing the telescope in more than one direction at once won't be available until 2031. So the MWA is well poised to really, really keep going in this transient space and make a lot of new discoveries. And, you know, maybe another factor of 2 collecting area, we could get close to SKA sensitivity. So I don't know how the bank is looking, but yeah, excellent. Just keep writing papers and motivating this. So I think the future is very bright for transients with the MWA. We're going to try and look for bright luminous things by scanning as much of the sky as possible. This does make our calibration and imaging a little bit challenging, but we are pretty on top of that now. And the nice thing is we can generally use, we're not trying to do precision measurements of the EOR here. So it's very much kind of a lucky imaging problem. And so with night, I'm hoping that we can eventually go into a mode where we are just continuously looking for transients, processing the data in real time, and then throwing it away so it has no impact on the archive. That's the goal. And thank you very much.
Thank you, Natasha. Questions?
All right, stunned everybody. Oh, okay.
So I was under the impression that subarrays were going to be available earlier. What is it specifically about that 2 substation arrangements?
Yeah, so subarrays can be used. So you can break up the whole, this is my understanding. If there's an SKA person in the room, you can answer this question. But subarrays can be used, so you can break the telescope up into smaller pieces and then use those to look at different patches of sky. But of course, their UV coverage will be horrible because you're using little pieces of the instrument. Great sensitivity, terrible UV coverage. Small field of view because the stations are really big. So not actually very good for like transient hunting where you want really good UV coverage, really good field of view. So substationing is where you take those stations and you break them up into smaller pieces themselves. And say you take, you know, the northeast corner of every station and you correlate all those together. And you take the northwest corner and you correlate all those together. Then you get a very sensitive, good UV coverage and multi-pointing instrument. So you can tile that enormous field of view. Obviously, this is just representative. Not all of this sky is actually up at any given time, but it's just to give you a flavor of how much sky you could cover. But that capacity won't be available and greater than 2. I mean, I need 16. So does that mean 4? I don't know. So I'm just saying that there's quite a lot of time. Full substation is here. So 2032. So assuming no slippage whatsoever, we can't do this with the SKA for 7 more years.
So that's the problem you get into even asking it to search for something you already know about. But in your introduction, you said you made new discoveries. What's going to be the chance of following up on the next new thing?
So this is about blind discoveries. This is with the goal of finding things blind with the SKA.
But blind discoveries of the kind of thing you just found.
Oh, absolutely. Sure. Okay. So yes, when we look in that parameter space, there could be all sorts of interesting things. I mean, we found some things that frustratingly people are calling galactic center radio transients, which is not a meaningful word, that have high circular polarization and vary on weeks to months timescales. What are they? Nobody knows. They're too luminous to be stars. They don't have clear optical associations. LPTs get a little bit more press because they're periodic. You can actually predict them, but these new transients are totally unpredictable. So I could give a whole talk on that. So we're already finding things, and actually there's already too many discoveries for the number of people that we have to follow them up.
Any more questions? If not, okay.
Okay.
Thanks
Thank you
again,
all.
Natasha.
Cheers.
Thank you, everyone. So that's the end of day one. We do have a later start tomorrow, so the first session will start at 11:30, but we do just ask you to get here a little bit earlier to make sure you sign in at reception. And the WebEx links for tomorrow and Friday will go out this evening. So thank you very much.